And we'll also provide the link to your next meetup on our meetup page. And next, Ota.
Thanks for that.
The floor is yours.
So thanks. This was nice presentation. I think it might be really good that we had this session prior to mine, because I think mine might be very related to what you were talking about. So this is good start. Okay, I'll share my screen now. So are we good? Can you see my screen?
Yeah, we can see it.
Okay, cool. Okay, thanks everybody for coming today to this Backend Meetup, and thanks for organizing it. And I think that I'll use this opportunity to tell you more about what Akka is, and I'll try to demonstrate to you a few interesting pieces of this technology and the framework and the ecosystem around it. And I'll guide you through a few practical examples of how Akka can really help you achieve greatness in this modern, highly distributed and highly connected world. And I'll try to also show you that these examples and this technology is not so hard or so challenging that you could not use it in one of your next projects. So with that said, my name is Otto Burgles. I'm a software architect and engineering manager at a company called Global Web Index. And in this company, I'm running the R&D lab that specializes into building new technologies for market research, and particularly in the domain of collecting data. I also run my own consultant. So if you have any problems that might be similar to what I'll talk about today, I can very likely help you with those challenges. You can read also my blog. It's called epic.blog. It has a couple of posts there. And if you find these topics interesting, you can find more resources there. And I'll try to and also try to push more content in the future there. You can also find me on these social channels. So if you have any questions and if you want to have better debate around these things, I'm more than happy to help you navigate that. This meetup was also now organized in partnership with this Scala Meetup Slovenia. So I'm trying to revive the Scala Meetup and try to connect people that are interested in Scala in Slovenia. So if you want to learn more, or if you want to ever speak about Scala or relevant technologies, I would like to invite you to this event as well. And thanks for giving me the opportunity to do this cross promotion as well. So what I do on a daily basis, described in a meme, would be this picture. So I go around and I explore very different technologies, very different concepts, and I play around with technology that might be relevant for our organizational success. So I play around with a lot of prototypes. I build a lot of proof of concept projects, and I explore a lot of different architectures as well. So essentially, I'm there to learn a lot about this stuff and then consult my team how we should implement these technologies or which technologies is actually needed for our use case. And the question, if we use this stuff in our daily lives at our business and for our development, and yes, the answer is yes. We definitely use Akka. We use technologies around it, and these technologies, if they wouldn't exist, we very likely wouldn't be where we are with our current project and the company as such. And the question that you should ask when you're learning about these new technologies should firstly probably be, what kind of problem are we actually solving, And the question related to Akka is, so what do you actually want to build, and what kind of challenges do you actually solve with these technologies? And well, the fundamental challenge that at least I am using Akka for is to get new data from mass amounts of people. So we use Akka as a layer for collecting a lot of data from a lot of people across the globe, and we do that in real time and in very distributed fashion. In order to get more perspective on that, I need to introduce you to more to what this company that I work for does. So company is called Global Web Index, or GWI for short. And this company provides what's called market research or market research insights. So that means that we collect a lot of opinions from people around the internet in different countries, and we then clean that data, correctly weighted, and correctly assure that the data actually presents the opinion of people. And we then provide a lot of technologies deeper into these opinions, and these opinions are then used for understanding audiences, understanding how the analytics works, and also help you understand how the market around your digital project shifts. So if you want to learn more, just go to globalwebindex.com or gwi.com, and you can learn more about there. We have a lot of very, very big companies, very big names that use us or integrate with us. So I think you will find also some data for your company there as well. And to go more directly to a product that me and my team is working at the moment on, the product is called PollPass, and it's essentially a market research platform with a specific that is designed for essentially surveying people. So think of it as Google Forms or SurveyMonkey Forms, but if done in a conversational manner, which means that instead of actually subjecting the respondents of people to surveys, we subject them to what we call exchange or conversation. And this stuff is then ran in real time, and it's distributed. Again, we do this kind of research in 16 plus languages, and we then also have a very sophisticated expression engine and logic engine that then can actually give the person feeling that once we learn more about them, we can ask them more relevant question, and that makes it for a better experience, and that also results in much better research. In practical terms, our product that faces customer looks like this. So you can see that you get asked questions, and very simple and very intuitively, you just select answers that actually represent what you think. And as you progress, the system learns more about you, so it can get real deeper into certain subjects, or it can skip certain other subjects. As, for example, we don't care about a particular individual. But in essence, on the surface, is very simple, very simple interface. Then behind the scenes, we also have tools where you can actually express this research, where you actually script the thing, where our researchers actually express what they are curious about, and this then translates into some kind of survey definitions that our system understands. On a high level, we have architecture that it looks very simple. So we have a lot of single page front app. That front end app then connects via WebSocket to our Akka cluster. And then we also have very traditional stateless RESTful APIs behind the scenes. And without this middle layer, this conversational layer that's not in the middle of your screen, it would be a very traditional web app or web application with API and front end in the middle. But since we have a challenge that for each respondent that is actually having conversation with our system, we need to keep a state of that conversation. it becomes a significantly bigger challenge on architectural level. So for each respondent that is any given moment having a conversation with our system, we have an actor that represents that state. The front end is sending messages to this actor, and replying messages back to the system. So you can see that it very naturally, we're dealing with a state. That state needs to be distributed, and we need to conduct this research on quite massive scale. Now, the future for us is quite challenging. You saw earlier that we're now conducting research in this conversation with text, but in the future, we are looking into expanding into voice technology. So what you saw earlier that was conducted with text is going to be conducted in a voice-like interface. So the system will actually ask you questions in the voice, and you will answer back in voice-like format, which means that we hope to elevate this experience even further. That again brings a lot of challenges with scaling, state handling, etc., etc. So in order to build such systems, you need to have a tooling or sophisticated tooling that can actually help you build these things in reasonable amount of time, and you need toolings that will help you avoid problems that were discussed, for example, in previous talk. So unreliable networks, massive scaling that you need to scale up in short amounts of time, systems that could never be down and that needs to be upgraded while they're running, and you obviously also don't want to have too much resources allocated in advance, because that, for example, will be very, very expensive with such scale. So we address these problems, like I said, with Akka and with this framework. And Akka is essentially a library, but it can also be thought essentially as an ecosystem, and I'll explain to you what I mean by this ecosystem in a while. What you should know about Akka is that this is essentially what's called the implementation of actor model. This is the programming paradigm that was developed by Carl Hewitt in 1937, and it's essentially a way of abstracting away problems of that you deal with in concurrent environments, with distributed environments, and it extracts away the problems with locking and thread management, etc., that you would have if you would not use such frameworks. The system was built, like I said, in 70s or in 80s, and it was implemented firstly in Erlang language by the company Ericsson, and the success of this thing also can be seen today. So you can have actor model implementation in very different languages today. And yeah, Akka is probably one of the most popular ones running on top of Java Virtual JVM or Java Virtual Machine. Yeah, you can get these actors in different languages, and why the Akka is so popular with Scala is that the Scala has a really great compiler, a very sophisticated compiler, and it's very flexible language, which means that DSL for building Akka was also neatly implemented on top of it. Now, what's in the Akka toolbox? So Akka is built for building simple, concurrent, and distributed systems. It uses two fundamental blocks for building these things. One is called actor and the other is called stream. And it also comes with all the tools that you need for building things like CQRS systems, event streaming, event sourcing. And for example, if you want to build your own CRDTs, you can also have everything already prepackaged for you. And this thing is also built in a way that it can be used in very high performance systems. So you can use it for systems where very low latency is required. and it has very small footprint, so you can use it for a lot of very different things. You don't have to use Akka just, for example, for server-side applications or distributed applications. You can also use it for, I don't know, desktop applications running on JVM. And although Akka is very popular within Scala world, the APIs and the spec and everything can also easily be used in Java. So if you have, if you want to use Akka but don't fancy Scala, you can use everything in Java. The company behind Akka is very committed to having APIs for both languages equally represented. Okay, now we're gonna dig a bit deeper into what's actually inside Akka. And like I said, the first piece of the big puzzle is Akka Actor or Akka Actors, and there are multiple ways how you can introduce people to actors. In this case, I chose to introduce you guys just through code, and I'll try to you why what certain pieces of code do and why system behaves as it does. So with that said, what you see on your screen is essentially one very small Akka application, and the code on your screen is essentially written in 2 blocks. On top you have 1 class, and on the bottom you have main application. On the top, this class is an actor that represents essentially a person. So it has a couple of attributes like first name and last name, but you can see that this class inherits from actor. Then it'll also implement something called actor logging, which is used for logging within actor. The only thing that you need to do if you want to use an actor in Scala or in Akka is you need to define receive method. So whenever you write an actor, you essentially extend actor and define receive method. Then in this receive method, you then define your business logic. So this is the only place where the business logic should essentially live. Now, on the bottom of the screen, if you look, we now have example of how you spawn different actors. So in this case, we create 3 different people, or these 3 different people are represented by actors. So there are 2 kids and myself. And once you spawn the actor, you get back actor reference. Actor reference is essentially, think of it as a pointer inside actor system. So think of it as a unique URL to an actor that could be essentially anywhere. And you need this pointer or actor in order to communicate or send messages to actors. Now, actors communicate only through immutable messages. So actor is isolated in a way that it can only communicate with outer world through messages by receiving messages and sending messages back. So in the following example, I have, for example, one pointer to our actor reference to this kid number 1, and I send him 3 messages 3 times, and these messages are sent asynchronously, and the actor internally will start doing something. So in this case, it will suspend or thread will sleep for 5 seconds. That will simulate the work that this actor is actually doing. And if the actor receives messages during this time, these messages are going to be stored in what's called actor's mailbox. So actor mailbox is essentially a queue, and the messages start piling up there. By design, actors are unbound. Actor mailboxes are unbound, which is that actor can receive as much messages essentially as you have memory inside your machine, and after that you'll start seeing problems. So messages just pile up, and once the actor actually can process these messages, they'll be consumed and the system will proceed. And on the bottom you can see that I'm also sending some more messages to the system, and on the bottom you can see that I'm sending this drink beer message. Now if actor does not know how to respond to message, these messages go into a special mailbox called dead letters mailbox, and it's a mailbox for messages that could not be delivered, and you'll get warnings if that actually happens. So actors only respond to certain kind of messages in general. Now, this is essentially the simplest example of how you create an actor that will do something. In this case, it will say it's eating ice cream. Once the work is done, it will say that the ice cream was eaten, and then it will start idling essentially and waiting for future work. Now, if we run this example, you can see that for example, one person has started eating ice cream, then another person has started eating ice cream. Then we got some message that was unable to be delivered because the system was not accepting it at the moment, or the wrong message was sent. And then you can see that the actor has actually consumed the message, and the green emoji was then presented. So you can see that how messages can be sent and how they're processed. Now, these actors essentially encapsulate state and behave differently depending on which state they are. So in previous example, I was working with Akka that is called Akka Classic. But in this example, I'm gonna show two examples with what's called Akka typed. So this is essentially the way of today working with Akka. The difference between classical Akka and typed Akka is that typed Akka requires you to define types, and the compiler will also keep you, the compiler will also assure you that certain states cannot be reached and certain messages could not be sent, and it will also help you assure you that things are type safe. It has also a bit more functional API that's traditional Akka, and it has an abstraction that's called behavior. And once you'll see this behavior popping around, this means that actor is actually behaving in a certain way, and that way is defined to this receive method. So in this case, we have state diagram on the top of your screen. This actor has two states. One state is idling, which means that it's just, I don't know, initialized. And in that case, it can receive message called eat ice cream. After it receives message eat ice cream, it goes into a state of eating ice cream. Once the ice cream is actually consumed, that will mean that 5 seconds will pass. It will go back into the idle mode. So you can see that you can have that you can define two different states. So for example, here idle state and eating state, and the actor will behave differently given which state it is. So the idea of self-defining these states is very, very easy. And you can also see that the way or from one state to another is done through a timer. So in 3 seconds, the message is sent and the switch from one state to another happens. And yeah, like I said earlier, if you use Akka type, you need to define commands, and they need to be more strict. So usually you won't send strings like I did before in the previous example. And the other big advantage and how Akka actually is a resilient framework is that the structure in which you organize actors is tree-like, which means that actors come in actor systems and they come in trees. So in this example here, I now define the family actor. This family actor has actor reference, so a unique URL. And then I also defined, similarly to previous example, 3 different actors, and they also have different URLs. And the actor that spawns the child actors can also observe what's happening with child actors. So for example, if one of these children that were created here on the bottom of this tree would die, the parent actor knows that, and he can spawn up again the child actor. And by these concepts, you essentially build resiliency into the system. So you cannot, or you won't corrupt or kill the whole system. You'll just partially drop parts of the system, and they can be rebuilt accordingly. So like I said, we define commands, and in this case, it's you can see this child context spawn. We create another child, and this actor is then aware of that. And if you want to communicate with these child actors, you again send them messages and back to these messages. You can see that this child function and first name actually will try to find that child with particular ID that was generated here from name. Now, if we run this example, so I created here a family actor. I create 3 people by sending the message to family, and then I instruct this eat cake commands, and you can see on the bottom of the screen that these people started eating ice cream, and then after 3 seconds they are done, and the message is then displayed with the green tick emoji. You can also see that the message that the actor received messages and it didn't know or was in a state that message was received in a way that it replied with "sorry, I'm still eating ice cream." So essentially it reacts differently based on the state. And like I said earlier, if you use Akka typed, the compiler will actually check what kind of messages are sent to the particular actor. And for example, this example won't actually compile because you're sending a message that is not part of the traits that we defined under family command. Okay, so that was essentially the short introduction to actors. But as you saw, the actors are pretty, they're very, very powerful, but it could get repetitive if you try to repeat similar patterns. So it makes sense to build higher abstractions on top of actors, and that will essentially make you more productive, and you can build more sophisticated topologies. You can build more sophisticated systems on top of it with better composition, again, with a more functional way. So I'll describe this example here. So we have essentially a client application that will try to read the temperature from a web service. It will do this in every 5 seconds. So every 5 seconds, we try to read a temperature of the air in a city. We get that through calling a web service, so external web service. Then we need to handle the response from that web service. Then we parse XML. Then we store the current temperature. Then we detect if current temperature is different from previous temperature, and then we compute if something has changed. So this is like, if I would describe this problem to you, you would instantly know how to do it in any kind of programming languages. And usually when this could be a good use case, and if you work simple application for yourself, like my predecessor said, the systems are today more complex, and you have things like network problems, etc. So in real world, the web service that you're trying to call here, might have network problems. It might be unreachable. Your network might be unreachable. So you'll have a problem there. So when you try to handle the response from this web service, that web service might return 500 error. You won't be able to process that thing. And then, for example, here we're dealing with a service that serves XML. Then you need to convert that XML into some internal representation that you can actually work with. Again, that XML might, for example, be broken. And then, you're dealing here with storing state. That state can be really big. It might be that you won't be able to actually keep that state in the memory. Again, a problem. And so it goes on and on and on. And, for example, in this case, you go into sleep mode for 5 seconds, you block, and then you go and then you repeat the cycle. But the problem might be that because you don't have any kind of circuit breaker or anything like that, you might repeat this, or you might, for example, DDoS the service that is, for example, already crippled, etc. So you can see that what began as a really simple problem on the surface, it's actually a very complex problem if you try to figure out all the edge cases, if you try to actually engineer this thing in a very predictable way. So with that said, this is the implementation done in Akka with Akka Streams, and I'll try to give you an example why streams are so powerful, and I'll try to explain to you why, if you leverage things like Scala, you can predict all these edge cases. So with that said, so here it starts with a source. So Akka Streams has three main components. One is source. Source is generating content. It could be, for example, file source that you can read content from a file. It could be a database source. It could be web service. It could be, in this case, timer that generates ticks, or it could be anything that produces value. Then it has the second part, which is called flows. They're essentially transformers from one data shape to another data shape, and then you have sinks, which are essentially the end outputs of where the data will actually flow in. And these are essentially three main blocks that you use here, and I'm going to show you what that means. So here we generate tick every 2 seconds, and the string called tick from this system. Then we actually call get measurement function that's defined here on the bottom of your screen, and then we output that what's the result from this web network call, and then we actually call another actor. We detect where we try to compute the actual change, and then we only care about the responses that are actual changes. So if any network problems occur, if parsing fails, if anything else happens, we don't care about. We only care, for example, in this case, for a happy path. And on the bottom, you can then see the output where we'll actually print this thing on the screen. And here you can see the method that's called get measurement. This is essentially Akka HTTP client that generate or issues requests, HTTP requests. It could be HTTP2, the external web service. Then it parses the response, it parses XML, and then actually tries to get, in this case, for example, number of temperature. And this is like you see the very simple Akka Streams allocation with that has got like very high level of abstraction. It can really easily be understood if you look at particular pieces. Now, sorry about that. So now it's possible that that these network requests might fail. So in that case, we're going to wrap this web request into what's called restartable flow. And in this case, with the flow, we replace that function that was calling external service with another flow. And that flow will essentially try to make these requests. And if any kind of failure happens, it will start adding delay, and it will generally back off with a particular algorithm that you can define here. So it will try to restore these things in several ways, and if everything else fails, then it acts essentially as a circuit breaker, and then the error will propagate further, and at some point you'll have to deal with this problem. So this is an example of how this application actually works. So here you see that the system is actually giving, measuring getting back the temperature from the service, and then I introduce synthetically delay between these requests to a gateway. So you can see that I get a bunch of errors, bunch of work that the system cannot reach the client, and Akka will then gradually start to back off and wait for a couple of seconds, so not to cripple the service and all that stuff. And once I remove that delay from the gateway, you can see that the system will start progressing and behaving completely normal and predictable. So this means that the system is much more resilient to network problems or problems of that nature. So like I said here and mentioned here earlier, this was done by the usage of Akka HTTP. This is Akka HTTP has two packages. One is Akka HTTP client, so for issuing requests like this, and it also has Akka HTTP server, which you can build which you can use for building highly concurrent and highly performant services that actually need to reply through HTTP or HTTP2. And these are essentially the blocks that you're going to use if you actually build web services. Again, you should not probably spend too much time building these abstractions if you are working on any kind of integrations. So for that case, there is a project called Alpakka, which is essentially a collection of sources, flows, and sinks for dealing with these external services. So for example, if you're dealing with processing CSV, if you're dealing with parsing some JSON, if you're dealing with calling gRPC services, if you're dealing with, I don't know, Apache Kafka or Pulsar or any kind of service like that, it's very likely that some people have already built a very good library for this, and you can just use that. So if you attempt on doing any kind of integration with some legacy system, you can probably find the package for this. So it's a very up-to-date collection of libraries that you can use, and they're built on top of Akka and Akka Streams. Okay, so I'm trying to be time cautious, so I'll try to progress a bit quicker now. The other example is that if you go now a bit back to where we were talking about Akka, where Akka is actually something that represents state, right? So previous examples, when we created an actor, that actor lived as long as the system was up. Once the actor system was shut down or JVM was shut down, the actor also disappeared, and that's perfectly fine. But if you want to build, concurrent applications, at some point you're gonna need persistence. So you'll need to store all this state that actor actually represent in some way. And for that use case, you use part of the Akka is called Akka Persistance. And Akka Persistance is essentially a way of persisting actor state and actor messages to a journal. And that journal is usually either Cassandra or some other distributed data store. And it looks like this. And I'll quickly try to explain what we have here. So this actor on the right side is an actor that is built for building survey definitions, for example, and it can get 2 commands. So you issue specifically commands, and these commands then generate events, and events are then persisted to this journal through Akka Persistence. If, for example, the actor would be killed or actor would be stopped, and then recovered, you can rebuild the state of the actor back to initial state from the storage, and it can proceed. So it's kind of like build representation out of events. And yeah, in order to use Akka Persistence, you need to use this Akka Persistent trait or class, and you need to define 2 methods. One is receive command that will actually do this effects, and it will mutate things. And then you also have receive recover, which is a method that's called when the Akka tries to rebuild the actor from the journal. And this is essentially, you can think of it as a CRS abstraction, yeah, you can use this thing to build some pretty incredible things. There is also Another layer or another library or another piece of Akka, which is called Akka queries, or which is essentially more about the read side of CQRS, where you can actually build representation. So for example, here we have one survey, but if you could also have list of surveys, and to build that aggregate, you can use the more sophisticated techniques in a asynchronous way. And yeah, this is how you have persistent actors. And similarly, you can see that the DSL for actually communicating with actors is exactly the same as it was with previous actor. You send messages and the actor can reply with the current state. Now, if you understand this building block, the next challenge then becomes how Akka is. And there are multiple ways how you can do that. The easiest way how usually you can start is what's called Akka remote. So for example, you can have one actor system on your machine and another actor system on another machine, and you can just reference the other actor and the communication would happen. But you know, we now live in the world of cloud and in the world of infinitely scalable applications and all that. So you can also use Kubernetes for that. And underneath Kubernetes, you can also use what's called Akka Cluster. Akka Cluster, in essence, would spawn out, for example, multiple actors and different actor systems. And the cluster would then be aware, the router would then be aware where particular actor exists in that system. So for example, if you talk to one in one node of the cluster and the actor does not exist there, you'll be rerouted to another node where the data actually lives, where the actually actor can be spawned out. So for example, in our case, when we have several conversations via WebSocket, it's important that the messages, if you have multiple open communication channels, they always flow to a single instance in the whole cluster. So that you don't have other challenges related to that. And if one cluster node goes down, the cluster will then try to rebalance and shift things around. Now, there are multiple ways how you can actually achieve this. If you use Kubernetes in your cluster, Akka clusters and Akka Discovery, you can also use Kubernetes APIs to do the discovery and load balancing, all magical stuff. So if you're actually curious more about building these kind of systems, I strongly suggest that you look into what. And I'm running out of time, but the examples of how you can achieve this are not that dramatically complex. And now, if you are on the other side, don't have time to actually work on building your own Kubernetes cluster, managing Akka cluster on high performance systems. And if you need to deal with a lot of data, but you don't have the resources to do these kind of things, now Lightband is also launching a product or addition to Akka ecosystem. It's just called Akka Serverless, which you can think of as a serverless technology for stateful application. So if you want to build stateful application, but you don't want to deal with anything else than your business logic, then Akka Serverless is very likely the system that will conquer things in the future, and it abstracts away all these things which I mentioned before. And yeah, it's now I think in open beta. So if you want to play around, I think it's a good time. And that's just kind of like the overview of the whole Scala or the whole Akka ecosystem. And I just wanted to give you not just a basic, but a bit more advanced overview how actors behave, how you can build better topologies and better systems with it, and that the toolbox is very big and very mature, and you can really build some very interesting and very powerful systems with it. I think that you can also the language in which that's used here and the underlying systems are also probably the technologies that you'll be able to use in the future to address things like broken networks and scaling and all the problems that you usually encounter when you try to build these systems. And I think it's once you grasp what things are and how you put things together, I think it's not that dramatically hard to compose things with it. And back to Scala. So these examples that you saw here were built with Scala. Scala as a language actually enabled us to build these very expressive things, and it also enables us to build, you know, things like when you saw type checking or compiler telling us that, you know, certain message could not be sent to an actor because it's typed. So all these things of the Akka and its compiler. So I could spend way more time talking why is that, but I think I'm gonna run out of time now. So with that said, this concludes my talk. And like I said earlier, if you're curious about Akka, if you're curious about Scala and other wonderful things that could be built with Scala, I'm now trying to reboot this Scala Meetup Slovenia. There is a meetup group that you can join if you haven't already, and there is also a Slack channel that is going to become more active. If you are curious about these things, please feel free to contact me, and I'll be happy to talk more about these things in the future with you guys. So yeah, that's it from my side.
Okay, thanks, Otto. We have a few questions. First one is from Matjash, which is, do you get type safety across both backend and frontend? So maybe Matjash, you can elaborate.
Type safety across. Well, there are multiple options. So I can go just a bit off from Akka's Akka talk that I talked about earlier. So you can, for example, today build projects that are written completely in Scala, and you can use, for example, Scala JS, which is a Scala compiler technology, if you want, that compiles Scala code directly into JavaScript code. So it's essentially similar to how TypeScript works. You write Scala code, and then with some tricks, etc., it compiles into JavaScript. And you can obviously use Scala on top of JVM traditionally in the backend. And then you can have a shared code or shared modules that you can define, and they can be, and that code can then essentially be used both on the front end and both on the back end. So there are examples like that. You also have like web frameworks that specialize into building more sophisticated glue and providing more things to achieve that. There's also a project called Akka gRPC that is for building gRPC based services on top of HTTP2 itself. So there are ways like that. Hopefully that kind of like answers your question. So there are ways how you can achieve that, but you know, these are still ways like you can probably achieve the same thing as you can with TypeScript and Node.js. Yeah. Hopefully that was my.
Yeah, I think.
When sending messages through, yeah, I think I answered. Yeah.
Yeah, I think you answered it nicely. Okay. The next one is from Per. How does Akka Persistance handle journal compaction? Or do actors always need to handle all events that ever happen on recovery?
I would say that it depends on your use case. So you have full level of control how you approach that. Usually what it happens is you implement two things. One is this, what you saw earlier, when you send issue commands and then you persist events into the event log. The other aspect of that is what's called snapshotting. So for example, on every 100 or 1,000 messages that you send to an actor, a snapshot will be created. and a snapshot is essentially state that is serialized into a binary format, and it's also stored in Cassandra. So if actor crashes, the recovery would first start from recovering from snapshot. So it would take that binary representation from snapshots table, initialize that, and then it will, if you need, go and roll back to through what's the difference between the events. So in general, recovery always happens from snapshots because it's way more performance. So you don't have to process thousands or millions of events. Yeah.
Okay. The next one is, I can imagine that building a new platform or on Akka is a lot of fun. Do you have any experience in introducing it into an existing legacy environment?
Introducing. And I hope I would be able to ask like a sub question. Is this like I said, if you have a Java shop and if you have people that are already way familiar with Java, you can use Akka and you can use it with Java. There is no, like I said, the APIs and everything is fully compatible. You can go into docs and you can see on the same example written in Java and equally in Scala. I think that their ergonomics are better in Scala, so that's why I prefer to use it like that. But if you have people that just want to stick with Java, I think you can still use Akka, and that's perfectly fine. So that's that. And you can, you can also introduce these things to your organization. I mean, you have probably some kind of containerization in your system, so you can easily package Akka applications into Docker containers, and you can ship that, and that works perfectly fine as well. You can even go as far as building, compiling your Akka application with GraalVM into a native image, and then you can run that, for example, even more natively or something like that. So there are ways how you can do that, definitely. But it depends on your use case.
Next one, I think this is the last one, is how is your experience with Cassandra? As we used Redis for Akka Persistance because Cassandra is hard to maintain.
You used what? Redis?
Yeah, that's what they wrote.
So usually you have a distributed system. So like I said earlier, this comes in a distributed fashion. So you have a lot of nodes, etc., etc. So it kind of makes sense that your persistent layer is also distributed, and it kind of makes sense that that you don't rely on single point for storing this stuff. And if you want to achieve better scalability, Cassandra also has these partitions and sharding, all that stuff that can really make your life easier. So for example, I can partition users that are from, I don't know, Europe in one cluster, and I can use keys, I don't know, usernames or whatever to do that. Or you get that kind of like fine-grained control, and you get resiliency and performance that you need for cases like I said earlier, writing a lot of events and then quickly persisting, that you usually don't get. I'm not sure if there is Akka Persistance plugin for Redis. I don't think there is. I might be wrong. But there is Akka Persistent JODBC, so which means that you can use any kind of database for storing these events. Previously, for example, we used Postgres for persisting events, and it worked well. So you don't have to use Cassandra. You can use, for example, like I said, Postgres. But if you have like a lot of volume, then you'll probably end up with the similar challenges that Cassandra solves more or less from the day one.
Yeah, there was a sub answer that
if you are building the stuff locally.
Yeah, sorry. Just wanted to say that there was this sub answer.
I'm saying that
there is a community-based Redis plugin.
Oh, okay. Yeah, there is also, you can also for local development, or if you want to build, for example, what you can do is you can use things like levels.db or rocksdb for persisting stuff. So you can also use that as a wrapper for Akka Persistance, which means that, for example, you have a node, and that node will then persist into a local DB that's located near that node, and then you would not have this distributed storage on top of Cassandra. So you can also do things like that. But generally, the implementation of how you the layer that actually does the persistence is pretty trivial. You have to implement few methods and provide your own implementation. You can essentially store wherever you want. But like I said, for production uses, Cassandra or Scala DB or whatever might be go-to solutions. But again, it depends on your use case.
Okay. Thanks, Otto. This was the last question. And yeah, thanks everyone for joining this meetup. Hopefully the next one will be finally in person, because these remote meetups are getting on our nerves. Otherwise, yeah, feel free to ping either me for a backend meetup if you have some cool topics, or Otto, like he mentioned, for the Scala meetup. I have also recorded this Zoom, so it will be shared on our meetup page, and also we will share the meetup link to the pair meetup. If you want to learn something, why not? And yeah, that's it. Thanks everyone for joining, and have a good evening.
Thank you. Thanks for organizing.
Thanks for having us.
Thank you. Goodbye.
Bye-bye.
Bye-bye.